Hi, my name is Jim and today's topic is parallel circuits. And this is a diagram of three resistors in parallel which are being fed by a voltage source V. And the way we define a parallel component is that one lead of one part connects to one lead of the other part, and the second lead of the first part connects to the second lead of the second part. If we only had one lead connected together, they would be in series. So that's the definition of parallel. And in this case, what we're interested in doing is several things, and one is finding out what the total resistance would be looking into the parallel network. Now what we need to know here, and this is in contrast with series circuits, is that the common parameter here is voltage. So voltage is the same across all parallel elements, and that's an important thing to remember. In a series circuit, it was the current flowing through the resistors or load or whatever, the lamps, that was the common parameter. So in this case it's voltage, and what we would do then is label this as I total, and that would be divided into three parts, I1, I2, and I3, and that would follow Kirchhoff's current law, which briefly stated says that the currents flowing into a node or a connection has to equal the currents leaving a connection. In other words, there can be no current leaks. And this is very similar to Kirchhoff's voltage law, which says that the sum of the rises in a circuit has to be equal to the sum of the drops. So let's figure out what the current here is, and we're just going to be using Ohm's law. I1 is simply going to be my voltage here, and I've assigned this a value of 12 volts. Divided by the resistance 2.7K, and that comes out to be 4.44 repeat milliamperes. And I've done the same with I2 and I3. So if I want to find the total flowing in here, what I'd simply do is add these up, and I end up with 11.15 milliamperes. So to find the total resistance then is straightforward. And again, Ohm's law, 12 volts divided by the current, 11.15 milliamperes, yields a total resistance of the network of 1076 ohms. So if I took an ohm meter, and you always disconnect power when you use an ohm meter, and looked in here, that would be the value I see relative to the tolerance of the resistors, which today are typically plus or minus 5%, unless you want to pay additional money for 1% or 0.1% or whatever. So let's take a look at the power in a parallel circuit here, and we'll be looking at the power resistor 1. And, well, since I have three choices to figure out power, it's V squared over R, I squared times R, or V times I. Either one will work, or any of them will work. And the one you want to use is the one that's the easiest to use. Now, if I didn't solve for the currents here, what would be the easiest to use clearly would be V squared divided by R. So I have elected to do that, and 12 volts squared divided by 2.7K for resistor number 1 yields a power of 53.3 milliwatts. And doing the same with power 2, 43.63, and power 3, 36.9 milliwatts. And then to find the total power dissipated by the resistors, as you can imagine, it's just the sum of the individual powers, and that comes out to be 133.8 milliwatts. So, if I were to elect to use V times I total, and I have to be careful of that, to find the total power dissipation, 12 volts times 11.15 milliamperes, which was our total current, would yield the same value of 133.8 milliwatts. Now remember, if you're doing this on a calculator, you may be getting some round off there, so close is acceptable. And what would be the power provided by the source? Well, that would be the energy, which would have to be equal to the power dissipation, which would be 133.8 milliwatts. So all's accounted for. The battery once again stores chemical energy, which is converted into electrical energy when there's a path for current to flow. So we can see in first look here is that parallel circuits yield well to Ohm's law to provide necessary current values, but one of the things we have to do is to find the total current flow, and it sometimes can be inconvenient and sometimes very difficult. So let's figure out another way. So let's think about resistance for a minute, and we talk about that, for example, of a 1/4 inch in diameter pipe compared to a 1 inch diameter pipe, and we can easily observe that the 1/4 inch pipe offers more resistance to the flow of water because of a smaller cross-sectional area than a 1 inch pipe. So what we can summarize then is to say that resistance is the opposition to flow, and in our case electronics be the opposition to current flow. But I also could look at it from a different direction, and that would be the conductance. So I could also say that the 1 inch pipe allows water to flow easier than would a 1/4 inch pipe in diameter. So conductance basically defines how easily current can flow. Resistance, how hard it can flow. Now, for example, let us say that this point is 4 feet from the floor, and it's also 4 feet from the ceiling. Let me make it 5 feet from the ceiling. So I could say that this is 4 feet high or 5 feet low, and it exactly defines this point. One references the floor, the other references the ceiling. The same it is here. They're referencing different things, but they produce the same result. So let's take a simple case here and let a resistor equal 10 ohms, and what I want to do is find the conductance. So this is going to be 10 ohms of resistance to current flow, and in conductance it's going to tell me how easily the current can flow. So the unit for conductance is G, the symbol is G, and the unit is Siemens, which is capital S, not to be confused with lowercase s, which is seconds. And the relationship is straightforward. The conductance is simply the reciprocal resistance. In this case, 1/10 ohms yields 0.1 Siemens, or 100 millisiemens. Contrarily, the resistance would be equal to the reciprocal of the conductance. So that's very straightforward, and you might be wondering kind of what good this is, but stay tuned for a minute here. So I've redrawn this diagram, and I have R1 and G1, R2 and G2, and R3 and G3. And now what I'm going to do is find the conductance of each one of these branches. And I'm going to do it the same way I did before, as using the reciprocal. And for R1 and G1, that comes out to be 370.4 microsiemens. G2 is 303 microsiemens, and then G3 is 256.4 microsiemens. Now what we can see from this is that the 2.7K has the higher conductance value. The 3.9K has the lowest conductance value. So to put that in English, it's easier for current to flow through this resistor than it is for this resistor or this resistor. So if we wanted to find G total, all we would have to do, the total conductance, is add them up, and we end up with 929.8 microsiemens. Now to find our total, what we know is there's a reciprocal arrangement in here, and just taking the reciprocal of our total conductance, we end up with, guess what, 1.076 kiloohms, exactly what we had before. Now the question probably on your mind is, why do we need to do this conductance stuff? And the answer for that, coming up on the next page, is we have G total equals the sum of the conductances, which we kind of went over before, and I can substitute in for that the resistor equivalents, which are based on the reciprocal. 1 over R total equals 1 over R1, and so forth. You can see the relationship. And then if I rearrange things, I can find R total with this here formula. 1 over parentheses 1 over R1 plus parentheses 1 over R2 plus parentheses 1 over R3, and so forth forever. So this is the general way of finding the total resistance when you have resistors in parallel. It doesn't involve current, doesn't involve voltage. It's simply the relationship of the resistors. Now, this is a formula that you need to memorize. You need to be very familiar with this because you're going to see it, well, like forever. So it's very important. But we have a simpler case, fortunately, of only having 2 resistors in parallel. So if I were to work this out, RT would be equal to this term, and note that this is just this with 2 resistors in it, and then I wiggled some things around here, found the common denominator, and then multiplied both sides by the quantity R1 over R2, and this is what we get for a formula for two resistors in parallel. This guy here, as you can see, is pretty straightforward. This is called product over sum, and it's useful. Oops, wait a minute. Yeah, all better now. Useful in inductors and capacitors in a different way when you get into AC circuits. So in summary, with this here, if you have a resistive network that is involves two or more resistors, this is the guy you want to use. And if you only have two resistors, this is probably the simplest one. Now, what's tempting to do is to solve for these two using this, and then to take the results of this and this using this formula also. So you'll be using this twice. And what you have to be careful there is the accumulation of error. So best do it right. This can be entered on one line in a calculator. It's fast. It uses the reciprocal button. That's when x raised to the -1. However, on a test, what you want to do is come up with all the intermediate steps. If your instructor is so inclined to give you partial credit, and you can see that you know the process for doing this, and maybe flip the decimal point or slip the decimal point or whatever, reverse digits, you can get partial credit for a wrong answer. So always leave a trail of what you do and leave it in an orderly fashion, not having equations written all over the place. When an instructor is trying to grade things and can't see the flow of thought, it doesn't take long just to mark the problem wrong and move on. So these are the two key equations that you need right here for finding resistance in parallel. And then in AC circuits it's going to be similar, except you're dealing with complex numbers. So you got to get this down in DC because AC is a little bit more involved. Okay, current divider rule, and what we want to find here is IR1. There we go. And this offsets Kirchhoff's voltage divider rule. So what we're going to do in this case is we want to find our total here, and I've assigned an arbitrary voltage V, no value to it because it's going to disappear in a minute. It's just a convenient tool. I total is flowing in, and we have the same as we had before with the branch currents for R1, R2, and R3. And what I can say about this using Ohm's law is that the total current flow, I, is going to be equal to the voltage that's across the total resistance, which are all of these guys in parallel. And I can also say that the current flowing through R1, and that's, say, the current that I'm interested in for some reason, is going to be equal to the same voltage divided by R1. So maneuvering things around a little bit, I see that the total current times the total resistance is equal to the voltage, and the current through R1 times R1 is going to be equal to the total voltage, and therefore, since they're equal to the same thing, this quantity is equal to this quantity as expressed here. One last step is, since we're looking for I1 in this case, it could be any I, so we want to find any current flow, is that if we combine and wiggle things around, we see it's IT times RT over R1. Now, this may look wrong to you, so let me back up a little bit in the series circuit. In a series circuit, the total resistance is always greater than the largest resistance. In a parallel circuit, the total resistance is always less than the lowest resistance. So this quantity here in parentheses is a number between 0 and 1. It cannot be greater than 1 because the resistance, total resistance, has to be less than R1. So when we multiply that through, what we would end up with is finding the branch current I1, and I didn't bother to do that in this presentation. But this is the general current divider rule that you need to be familiar with, as you would be with the voltage divider rule. RT is in the numerator, and just remember that it's lower than the lowest resistance in the circuit. And that's a good sanity check on a test. you get a total resistance which is greater, you made an error. So for cases with two resistors in two slash lines here, and that's the short abbreviation for parallel. On the keyboard they're vertical bars, forgot what they're called, what the name of the symbol is. But this would be the symbol here of R1 in parallel with R2. So in this case we're going to start with our general formula for current divider rule. And I have RT here, and what I know is that the product over sum for two resistors will also give me RT. So I've just written that down here for R total with two resistors, and then what I've done is I've substituted the product over sum for R total in the numerator. Next step on that, and I've taken this and recopied, and this is the same as this guy here, and I multiplied by 1, meaning 1 over R1 divided by 1 over R1 to get rid of the R1 in the denominator. And I end up with, in the numerator, R1, R2, and R1 times the quantity of R1 plus R2. And dividing out the R1s here, what we see is I total is equal to R2 over the sum of R1 plus R2. So if you have two resistors in parallel and you need to find the current through, in this case, I1 would correspond to, let me put a little parenthesis here, R1, is you would end up with this formula would probably be easier than the general formula. Now, there's a gotcha in here. In voltage divider rule, the voltage across which you want the part is in the numerator. If I want the voltage across R1, R1 would be here. In the current divider rule with two resistors, it's the other guy that's in the numerator. I want the current through R1, but R2 is in the numerator. You have to be very careful of that because it exactly contradicts the general theme of voltage divider. So that'll conclude with regard to parallel circuits, and then our next stop will be series parallel, and then what we'll be doing in that is using both of the analysis methods to figure out a network that has resistors in series and a network in parallel. And that probably will be the most challenging component and the most important component in the course. So that'll conclude, and thank you for watching.